In the last lecture, you have seen linear interpolation using Lagrange basis polynomials. In this video, we will proceed with showing you some characteristics of these polynomials, resulting in Runge's phenomenon. Let us start with a function of a single variable x, as shown on the slide, and applying Lagrange interpolation using 3 data points in combination with an equidistant distribution on the interval -5 to 5. Given these 3 data points, we can use the second-degree Lagrange interpolation polynomial. Note that one of the constraints on this polynomial is visible in the figure on the slides. The values of the function and the L2 polynomial at the interpolation points coincide. When we take a closer look at the accuracy of this approximation, we might argue that this is very poor. We see that the blue continuous line and the dashed line only coincide in the 3 data points. And one can wonder if the accuracy improves when the number of data points increases, for example to 5 data points, still demanding an equidistant distribution on the interval. Respecting the requirements of higher order Lagrange interpolation and maintaining some sort of symmetry in the graphs, we can change the previous L2 polynomial to the L4 polynomial. At the 3 points in the center of the graph, the approximation appears to be better compared to the approximation in the endpoints. This raises the question, what happens when we continue this process? When we have 9 data points, we use the 8th degree polynomial. When we use 17 data points, we end up with L16. In this case, we see that the approximation in the center on the interval -2 to 2 appears to be good, but outside the interval it is not. The oscillations of the interpolation polynomial near the boundaries of the interval are known as Runge's phenomenon. A problem of oscillations at the edges of an interval that occurs when using polynomial interpolation with polynomials of high degree over a set of equidistant interpolation points. This brings us to the next question. Can we avoid Runge's phenomenon? To start, let's remove L16 with all the oscillations. Now you will see how these oscillations can be minimized by using nodes that are distributed more densely towards the edges of the interval. A standard example of such set of nodes are the Chebyshev nodes. In your book, you can find the formula which describes these points. Using Chebyshev nodes, a continuous function, such like the dashed line on the screen, can get a good approximation using more data points. Note that we still use a Lagrange polynomial, only now with a different set of nodes. Another way to avoid Runge's phenomenon is to use a technique which can be used in the case when we have measurement data. In many cases, these are equidistant data points, such as measurements on fixed time intervals, so we want to avoid Lagrange polynomials due to Runge's phenomenon. Instead, one commonly uses so-called splines. A spline is a piecewise polynomial that is connected in the nodes. For now, we only consider splines of degree 1, which means that any polynomial in the spline has at most degree 1. So the nodes are connected with lines. Consider the nodes as shown on the slide, as a partition for the closed interval a to b. In this video, we're only going to approximate continuous function, which basically means that these functions do not contain jumps. This is denoted by f in C on the closed interval a to b, and is necessary to assure the desired connections in the nodes. The interpolation spline of degree 1 is a piecewise function S and is given by the following expression. So, for the first half-open interval x0 up to x1, we have the first linear polynomial S0 of x. For the second half open interval, we have the second linear polynomial S1 of x. And we continue this until we have covered the entire interval up to Sn-1 of x. When we're going to plot these piecewise polynomials using the 17 data points seen earlier, we get the following approximation. As you can see now, the spline of degree 1 is a better approximation compared to the L16 with all the oscillations seen earlier. Even more, for 9 nodes, the spline already outperforms the Lagrange polynomial. Note that for the splines of degree 1 we need piecewise linearity, and we also need a continuous connection in the nodes as mentioned earlier. We can wonder how many conditions are necessary to determine all unknowns in the piecewise linear splines and how to actually determine these splines. Well, the answer to those last questions will be the topic for another time. But for now, we will take a break. Bye!